Hello everyone, my name is Billy Frans Marcelino Purba. Today and this time I will read my presentation is entitled Mechanical Properties and Strengthening Mechanics. In French, Metalurgi for the non-metalurgy second edition, edited received by Arthur Tirta. Topic. The first topic is mechanical properties. Second, strengthening mechanism. Um, Solid solution strengthening, effect of grain size, cold working, and back to the turbulence master and other important strengthening mechanisms. Mechanical properties. When a force or combination of force are applied to a material, the material responds by deforming or scattering, often in a complex manner. For example, when a being jumper hops off a platform, the butt, the bulk of fits dramatically, and the same time its cross-sectional area decreases. Under normal, crease contains the bounce or safely prevents the jumper from hitting the ground below. While this example describes a type of deformation that is readily visible, often the formation of the type cannot be observed this easily, but it does still take place. For example, a wire comes from the end of a steel wire will cross the water to the street and it cross-sectional area to decrease, but the amount of deformation is not readily observed without performing careful measurements of the length and diameter of the wire under load. Mechanical properties describe the relation between the stresses acting on a material and the resulting information the material undergoes as a result of these applied stresses. Different types of the tests which use an applied force can be employed to measure of mechanical properties as well. Additional examples of such properties include the elastic modulus, hardness, vertigo resistance, and fracture toughness. These, these are described substantially in more detail. A short list of the important types of mechanical properties includes: first is hardness. The second, linear elastic. Three, yield strength. And then ultimate strength and vertical strength. Next, impact toughness. And next, fracture toughness. And next, hex temperature, heat deformation, and stress fracture, where heat temperatures cause metals to permanently deform as a function of time, damping properties, and wear resistance properties. Elasticity. In the elastic region of the engineering, stress-strain curve in Figure 2. Stress is proportional to strain. This region is the straight line then that can be seen on the left-hand side of the stress-strain. When a crystal is stirred by an internal of external lattice, strain in response to the applied stress broke the relative movement of the atom. When bullet is removed, the crystal or object will return to its original size and shape, provided that the bonds between the atoms in the crystalline lattice are not separated too far. When this provision is made, the strain is elastic. The crystal or object has sustained elastic deformation, and the amount of strain is directly proportional to the amount of stress placed on the crystal or object. This law proportionally is called Hooke's law, or after Robert Hooke. Next, plasticity. The point at which plastic deformation or yielding is observed to begin the strain depends on the sensitivity of the strain measurement. With most materials, there is a gradual transition from elastic to plastic behavior, and the point at which plastic deformation begins is difficult to define with precision. In tests of materials under initial body, the three criteria for the initial reading have been used: the elastic limit, the proportional limit, and the yield strength. Like the picture, typical tension strength curve for a style as the limit points A is proportional limit and point B is yield strength of offset 0 to C. Yield strength 0 is the intersection of the stress strain curve with the strain axis. Next, drawing. Creep deformation. Creep deformation refers to time-dependent plastic deformation that occurs when a material is subject to constant nominal stress. The rate of creep deformation depends not only on the magnitude of the average stress, but also on time and temperature. Continuing creep deformation over time ultimately leads to creep rupture, also known as stress rupture. Fatigue. The tendency of a material to break under conditions of frequent stress is called fatigue. Fatigue is different from the ductile fractures that easily result from the growth, tension, and creep loading of most metals. Instead, a fatigue fracture is caused by the propagation of crack that initiate at a single point or at a few points in the material. And fatigue fractures are almost always brittle fractures. Most, most parts and fatigue specimens contain points of stress concentration such as surface roughness or change in your input or specimen section, at which stress is concentrated and where fatigue cracking initiates. Toughness. Toughness is the ability of material or to absorb an impact or shock load without fracturing. Specimen and load geometry, scale, and the manner of load application are all important in toughness determination. For dynamic or high strain rate loading condition of land or notch or point of stress concentration is present. Notch toughness is ascertained by using an impact test, such as the Kelpie impact test. Now the next effect of grain size. Grain boundaries are effective obsolete to slip because the slip of this collision in the lattice of individual grains cannot easily cross the high energy barrier of grain boundaries. Instead, these collisions are blocked and piled up the grain boundaries. Breaking of grain boundaries exceptions occur when environmental factors cause a weakening of the grain boundaries. High temperatures, for example, can have a much greater effect on the weakening of graining boundaries than on the more regular array of atoms contained within the crystalline grains as not. When temperature increases, there are risks of point at which the grains and grain boundaries actually strengthening finish. The underlying structure of metals and alloys, the atomic structure of microstructure, have an important bearing on their strength, ductility, and toughness. Strength of materials can be improved in various ways, as described in the following section. For example, a microstructure with finer grains typically results in both higher strength and superior toughness compared to the same alloy. With physical larger grains, other strength mechanisms are achieved at the expense of lower degree and toughness. Thus, there might also be trade-off between strength and victory, depending on the material, the application, and the microstructural mechanism of strengthening. Solid solution strengthening. Solid solution strengthening is a mechanism that increases the strength of a metal through the careful addition of specific alloying elements, the insertion of substitutional and or interstitial alloying elements produce strength in the crystalline lattice of the host solvent structures because the solid atoms typically have a different size than the host atoms, and the picture is small substitutional atom like this and international atom and large substitutional effects of grain size. Grain boundaries are reflected or obvious to slip because the slip or discohesion in the lattice of individual grains cannot easily cross the high energy barrier of grain boundaries. The said discohesion are blocked and pile up the grain boundaries. Grain size plays a significant role in determining the mechanical properties of materials, particularly metals. The effects of grain size on the properties of a material can be understood through the Hall-Pitts relationship, which describes the relationship between grain size and yield strength. Cold working. Cold working refers to the process of altering the shapes and properties of a metal by subjecting it to mechanical stress at temperature below its recrystallization point. Unlike hot working, which involves shaping metals at high temperatures, cold working is performed at a near room temperature. Cold working techniques include processes such as rolling, forging, growing, bending, and extrusion. These methods can be used to improve the strength, hardness, and surface finish of metals while maintaining dimension accuracy. Cold working can also introduce residual stresses into the material, which might need to be relieved through subsequent heat treatment process. Some common applications of cold working include the production of sheet metal, wire, bars, and for use other metal components used in industries ranging from automotive and aerospace to construction and electronics. Cold working is favored for its ability to produce precise shapes and dimensions with excellent mechanical properties. Other important strengthening mechanisms. In addition to grain size, several other strengthening mechanisms play an important role in improving the mechanical properties of materials. The first is solid solution strengthening. Second, precipitation. The first is solid solution strengthening. Second, precipitation hardening or egg hardening. Three, grain boundary strengthening. 4. Wall hardening or straining hardening. 5. Texture strengthening. And 6. Transformation induced plasticity or thread and twinning extruded plastic or thread. And 7. The last is grain verification. Thank you for attention and see you again.